is the president and chief internet evangelist for Google. He contributes to global policy development and continued spread of the internet. He's widely known, as you heard before, as one of the fathers of the internet. I'm also curious to know who the mothers were, but perhaps he can tell us. He's the co-designer of the TCP/IP protocols and the architecture of the internet. He served in executive positions at MCI, the Corporation for National Research Initiatives, and the Defense Advanced Research Project Agency, and on the faculty of Stanford University. He's a recipient of numerous awards. In fact, we could take the next hour and walk through the awards that Vint has gotten, but they include the U.S. Presidential Medal of Freedom, the U.S. National Medal of Technology, the ACM Turing Award. He's an Office of the Legion of Honor, and he holds 29 honorary degrees. And we had a small dinner with Vint last night, and I think one of the things that I find incredibly compelling about his work is that over this long arc of his career, he's focused on those communities, and there are 3.5 billion people that don't have access to the internet. And in all of these various roles, he's kept that issue at the forefront. And he's kept that issue at the forefront for all of us as well. With that, I'd like to welcome Vint Cerf up.
Well, good morning, everyone. Whoops, as I destroy whose ever laptop is sitting here. I always get nervous when people clap before I've said anything because I think I should just sit down because it won't get any better than that. First of all, I have to tell you that CENIC in some ways is kind of a well-kept secret because I wasn't paying much attention, didn't notice it, I confess to you, for quite a while. And then it started bubbling up on my radar screen. And I love the acronym CENIC because think about the other one, SCENIC. And as I look out at this audience and I hear about the things that you're doing, it really is a scenic tour of the effect and power of networking of both kinds, the technological kind and the people kind. And you guys represent just an extraordinary, rich, and devoted group of people who want to make more network happen and make it happen better for everyone. So this diversity that's here today and the diversity that you're addressing is really resonant for me anyway. I want to endorse what Louis said in his opening remarks very much. Another thing I wanted to acknowledge is Hans Vanner Brown's work on the HP REN, the High Performance Wireless Research and Education Network. Some of you will know that he was the chief engineer for NSFNET, which is where I got to know him. And his work with HP REN has just been another example of just incredible dedication and creativity. And now, of course, it's become an increasingly important part of the CENIC activity, especially as you start looking at the possibilities of wireless extension to the existing network. It's a lesson that we've learned at Google as well. Our access efforts to dig up streets and pull fiber taught us that that's a fairly expensive proposition. And so we've also started to look not only at radio, but optical extensions, free space laser extensions to internet operation. I thought also, before I actually get into my prepared remarks, I wanted to mention another organization with which I am affiliated. It's called the People-Centered Internet. Mei-Lin Feng is here, and I don't know if Mei-Lin is here. There she is. She's waving in the back. Mei-Lin is the co-founder of the People-Centered Internet. We're very focused on the same kinds of thing you are, which is how to make the internet more useful for people all around the world, especially the ones who aren't connected yet. David Bray is the executive director, and he was the former CTO at the FCC, but chose to join us at PCI as well. I also wanted to recognize a few other people. Look, there's a lot of old friends here, and I do mean old, but and I'm one of them. But there are a few that have become incredibly relevant for my current efforts. One of them is Matthew Rantanen, who's over here waving his hand, part of the San Diego Tribal Digital Network, and Steve Hooter, who's sitting next to him. And David Lassner, who's over here from the University of Hawaii. These guys are very focused on trying to extend internet access to places where it isn't, and I want to acknowledge how much help they've been in that process. So although the announcing slide said, the arc of the internet and all that crap, I decided that I would just start with this unfinished internet and argue that, in fact, we ain't done yet, in spite of the fact that this is well over 45 years and counting. So I'll take you back just briefly to the predecessor network. I bet that there are a number of people in this room who were part of the ARPANET project and were connected to it as far back as 1969 or 1970. It just started with a 4-node packet switch net, and the idea was to figure out whether we could make diverse kinds of computers talk to each other across a homogeneous network. And that was a very important and very successful enterprise. It taught us a great deal about architecture, it taught us about layering, it taught us about end-to-end concepts and things like that. But it was just a single network, and so there was work to be done. This is what the packet switch looked like. Some of you may even have been at UCLA, where they've got one of these things. It's the size of a refrigerator, and when Bolt, Beranek, and Newman delivered it, it was delivered in this very heavy metal container because they knew it was going into a highly hostile environment. Bunch of undergraduates and graduate students, and this is worse than the military ever anticipated. So that's what it took to do packet switching back in 1969. And this is how primitive the system was. You'll recognize John Postel, Steve Crocker, and Vint Cerf. It took us 8 hours to set up this shot for Newsweek magazine in 1994. I mean, we had to go find the zucchinis and the yellow squash and empty the coffee out of the tins and then draw all the background pictures. But the reason that we did this shot, carefully posed, is that if you look carefully, you can see this network would never work because it was either ear to ear or mouth to mouth, but it was never mouth to ear. And we figured that this would be a great geek joke for the people who actually understood anything about networking. So some of you will also know that Bob Kahn started the packet radio program as a way of bringing computers into command and control in mobile vehicles. So we had these cubic foot packet radios that cost $50,000 each. So those are the white things that you see stacked up there inside the SRI packet radio van. This is a completely unmarked van with a stacked dipole array antenna sticking up the top. And it used to drive up and down the Bayshore Freeway, taking measurements of the effects of shot noise and things like that. And there's a story that I wasn't there, but one day they pulled off to the side of 101 and parked. And the driver, another engineer, gets out and goes around to the back. And they're all inside, doing all these measurements. Some police car comes along and notices this unmarked van with the thing sticking out the top and nobody in the cab. So he goes and he knocks on the back door. They open it up and he sees all these, bushy bearded guys with computer equipment and displays and everything else. And he says, "Who are you?" And they say, "Oh, we work for the government." He says, "Which government?" "But officer, we were only going 50 kilobits a second." Well, a little while later, in 1977, we had the opportunity to test the first 3-network test of the internet with a packet satellite net, which Bob Kahn also worked on. I think that was initiated by Larry Roberts, who also ran, of course, the ARPANET project. So at this point, the ARPANET spanned all the way across to Europe by way of an internal satellite link. We had the packet radio system running in the Bay Area. And we had the packet satellite net over the Atlantic linking the western part of Europe to the eastern part of the U.S. And so this is pretty exciting. By this time I was at ARPA, and I wanted to be able to demonstrate that the TCP/IP technology would actually link these 3 different kinds of nets together with different data rates, different error rates, different delays and latencies, and things like that. So I was very excited when this actually worked. We had packets that were being transmitted from the packet radio van through a gateway into the ARPANET all the way to Europe, back down to UC, University College London, then out of the ARPANET at that point into a gateway into the packet satellite net, and back over the packet satellite system to the east coast of the U.S., and then back into the ARPANET, and then all the way across to Los Angeles to USC ISI. So it's about 400 miles from San Francisco to USC, but it was about 100,000 miles for the packets because they went back and forth across the Atlantic and up and down through 2 synchronous satellite hops. And it worked. And I remember jumping around saying, it works, like it couldn't possibly work. It's software, and it's a miracle whenever software works. So I was very happy about that. Of course, then the NSFNET comes along and just explodes across the academic landscape. The NSF deserves enormous credit for what they did. Not only did they build the NSFNET backbone, but they also underwrote the cost of 12 or 13 different intermediate level networks, which was I would say an effort-saving tactic because they didn't want the guys running the NSFNET backbone to have to work directly with 3,000 different universities. So they had them deal with the intermediate networks, and the intermediate nets dealt with the universities. So it was a very clever multi-network architecture, and of course made possible by the Internet's protocols. Of course, this is what it looks like now. It's all very colorful. It spans a substantial part of the globe, including the South Pole, I might add. The purpose of this picture partly is to draw attention to the fact that there are lots of different networks. We call them autonomous systems. They're all operated independently, just like CENIC is. They have different business models. They have different equipment. They have different software. They decide who they interconnect with on their own. There's no dictated regime for that. Sometimes it's a peering arrangement with no exchange of money. Sometimes it's a transit arrangement where somebody pays. It's just an amazing variety of different diverse elements, but they all work together because of the protocols. And so this is a good example of the power of standards. And I want you to keep that in mind, this power of standards, because as the Internet continues to unfold, our dependence on shared and newly evolved standards is going to be very important. So here's some examples of unfinished business, and I'm sure you have a longer list than I do, and I don't propose to walk through every single bullet point here, but I want to emphasize how critical further development really is. And we all have experienced some of the negative, the downsides of Internet's penetration into the real world as opposed to the academic world. Here's the problem. I thought at the time that lowering the barrier to access to Internet, the ability to inject and to get information from it or to put information into it, was going to be a huge help because people know things that not everyone else knows, and the ability to share what you know is very compelling. And after the World Wide Web popped up, in, late 91 when Tim Berners-Lee first announced it, and then Mark Andreessen and Eric Bina did the Mosaic browser around 92 or 93, and then Netscape Communications came along, the World Wide Web became this terrific avenue for the injection of and access to information. In fact, there was such an avalanche of content that flowed into the net that nobody could find anything, so search engines came along like Yahoo and Google and Bing and so on, in order to help people find stuff. So I thought, wow, this is great. Drop the barriers to zero, let everybody share information, and everyone will be so much better off, except for one thing. Shakespeare was right. Not everybody has positive motivations. That's why we still read Shakespeare's plays. So we discovered there's a subset of the population that actually wants to inject malware and misinformation, launch denial of service attacks, and do all kinds of other, to commit fraud, all these other bad things. And so now we have to figure out how to protect the system from ourselves in some sense. And some of that will take technology. So we need to have strong end-to-end authentication in order to verify the pieces of the net and the parties who are playing in it. We need to protect people's privacy and their confidentiality. We obviously have to deal with the expanded address space. I hope everybody here recognizes that IPv6 is really needed now, finally. It only took about 22 years or so to get to the point where it's about 30% implemented. I mean, this is, of all the frustrations in the Internet, that's probably my biggest one. It's kind of embarrassing, too, because when Bob and I started this work, we actually did a calculation to figure out how many addresses we should have on the Internet. Remember, it was just an experiment. We didn't even know if it was going to work. So we said, okay, let's see, how many networks should there be per country? Oh, but we knew this had to be global because it was supposed to support the U.S. military and they had to go anywhere. So we started with the presumption that it would have to be in every country in the world. And then we said, how many networks per country? And since we just finished the ARPANET, this is 1973, we guessed that there should be at least 2 networks per country, so there'd be some competition. And, well, look, I mean, we're talking national scale stuff. I mean, it's not cheap. So we had 2. And then we said, how many countries are there? And we didn't know, and there wasn't any Google to ask. So so we guessed at 128 because that's a power of 2, and that's what programmers think in. So we said, okay, 256 networks. And then we said, how many computers per network? And we thought, well, go for broke, 16 million, that's 24 bits worth. So we had a 32-bit address space, 4.3 billion terminations if it was densely populated, which was more than there were people, I think, in 1973. So I thought at the time that if this worked, that would be the experiment, and then what we would do is build a production version of it after we demonstrated that it was feasible. The trouble is the experimental version escaped around 1989 and got into public use with 3 networks, the UUNet, PSINet, and SurfNet down in San Diego. And so we've been running the 1978 experimental internet for 40 years or so. So it's time to do IPv6. I hope everybody recognizes that, especially because we've got all these devices that are going to show up, the Internet of Things, with programs in them, cyber-physical systems, mobiles, and everything else. I also have a really long rant, which I won't go into today. It has to do with my fear that a lot of the digital content that we create every day is going to evaporate. And the reason is fairly simple. Some of you probably still have 5.25-inch floppy disks, 3.5-inch floppy disks, but you might not have any readers that can read them. And even if you had a reader that could read it, what you end up reading, which is what I did a few weeks ago with a 3.5-inch floppy reader plugged into my Mac, I actually got the files out, and they were a bunch of WordPerfect files, but I didn't have WordPerfect running on the Mac because that. So we have this problem that not only do we have to find a way to preserve and read the bits, but we also have to run the old software to make sense out of the bits. And if you're thinking 100 years or 200 or 500 years ahead, the question is, what will people do with those bits 100 years from now? Think of all the photographs we take with our mobiles, and we think, well, they're digital, they'll last forever. Except what if they don't? And what if the formats and things like that aren't remembered, or nobody knows how to decode them? It gets worse when you start looking at interactive stuff, whether it's video games or spreadsheets or even document editors, when you need a piece of software to do something with those bits. So you may end up having to emulate old hardware to run old operating systems and run old applications in order to interpret the bits. Now, I think there's a big issue there technically. There's also a big issue with regard to the cost of maintaining storage of those bits. And I'm not advocating that we should save everything, but I am advocating that if you had something you wanted to save, there should be a way to do that. And finally, there's a business model. I mean, if we do decide to store bits for long periods of time, how will we pay for that? What will be the business model that extends that? And I think libraries and universities may have a big role to play, since they have been the archives of much of our knowledge over in the past. It's kind of embarrassing, by the way, when you think about the way in which we have preserved information. Think about the cuneiform tablets that come from the Babylonian and Assyrian time. They were not intended to last very long. They were mostly just warehouse records on clay tablets, but the warehouses burned down and baked the tablets, so they became a really resilient way of remembering things if you can still read cuneiform. And as you go further into, closer to our time, you get other media like vellum. I mean, a lot of sheep died, but the result was to preserve a lot of Greek and Latin material, which has lasted over 1,000 years. And if you keep looking at the media, then you get rag content paper, which holds up pretty well for several hundred years. And then you get crappy paper, which comes around 1800, but made out of wood pulp, and which doesn't last very long at all. And then you get digital media, which we're so proud of, and if we're lucky, they last 20 years or 10 years or something like that. So somehow we've gone backwards in terms of preserving our content and knowledge for the future. So we have work to do. There's another problem, and that's stable identifiers for digital things. If you look at URLs, you realize they have embedded in them domain names. And the domain names go away if you forget to pay the rent. or if your company goes out of business. So all the URLs that reference content in the internet may no longer resolve. And you all had this experience. Even a printed paper with references in it that has URLs, those references may not resolve, in which case the underlying basis for a publication may no longer be accessible because somebody forgot to pay the rent on their domain name. So we really need to go invent a new persistent set of identifiers that will never go away, get permanently bound to digital content. Bob Kahn has one idea for that called digital object architecture. We really need to go deal with that. Now, you're already much involved in the broadband, wired, and wireless access to the internet. I congratulate you on that and encourage continued work in that space, especially this idea of just making the entire state of California one gigantic wireless mesh, which I think is a really fascinating idea. The last point on this slide is the notion of open software-defined networks. Now, I will confess to you that the first time I heard the term software-defined network, I thought, well, it's another one of those buzzwords, right? It's always been software, right? Every router you ever met, every packet switch you ever met was full of software. But this is actually a little different in two respects. First of all, open source, which is not the case for much of the routing equipment today, which is considered mostly proprietary. But the second interesting thing is the switching mechanism itself. You've started to see, and maybe you're already using, these hardware switches that basically have the ability to switch anything, from going in one port to some other port on the other end. But it uses software to decide how the switching is being done. Like Barefoot Networks, for example, has a 14 billion element chip. It's a great honking big thing. I'm astonished that it works at all, let alone with any yield. But this thing can do something like 4,000 instructions per packet flowing through any of its channels, because they have 32-step pipeline that lets you look at various parts of the packet as it flows through the system and then gets switched out the appropriate output. So this idea of being able to program the switch to do interesting things, looking at all the bits of the packet potentially, not just the address bits, is a very powerful idea. And so I'm beginning to pay more attention now to SDN as a very, very interesting and fruitful area. I confess, Louis, that I may be rattling on longer than you intended. It's okay, all right? It's the old farts like me just kind of get to rattle on for a while, so I'll rattle a little more. I've already mentioned the Internet of Things and artificial intelligence and machine learning. I have been preaching to my engineers at Google and now Nest and others that we need this collection of features for all the software that animates these devices. Reliability. Who the hell wants a device that isn't reliable and you're relying on it to run your home and things like that? Second, safety. Why would you want to bring a device into your home or your office or your business that wasn't safe? And how do we demonstrate that? Privacy. I mean, you don't want cameras in your house that were intended for security, but which anybody could look at. So privacy is important. And to say nothing of the data streams that are coming from these things. Even the temperature coming out of your HVAC control system could turn out to be a security vulnerability, especially if it turned out that somebody could see the temperature readings for a period of 6 months or so. You might be able to figure out how many people live in the house, when do they come and go, what are their diurnal patterns, and is anybody home? And so that data needs to be protected. Similarly, all the cameras and the other kinds of things, and the actual control of the access to the house if you have a security system. There's an interoperability issue, which I think is very important, because you don't want to end up buying different brands of devices and discovering that they don't interwork with each other. We're back to standards again, which are desperately needed at multiple layers in the architecture. The data content, the control system, the underlying transport mechanisms all need to have some kind of interoperability. Otherwise, it's just chaos in the house. And then autonomy, and by this I simply mean that you don't want your house to stop working just because the internet connection is broken. Because it's just that's a bad design. So there has to be something that works locally, independent of the availability of the internet. And I guess I'd like to mention one other thing about this class of object and that is scalability. If you think for a moment about a house that's got 100 things in it, imagine sitting there and typing IPv6 addresses for half an afternoon to get them configured. Nobody wants to do that. Or if you moved into another house that had 100 devices, now you have 200 devices to configure. We got to find ways of scaling this so it works more easily. And that's just the residential case. What about the business industrial case where there are 10,000 devices that need to be configured? So again, we need to pay a lot of attention to scalability. I mentioned machine learning and artificial intelligence, and there's another hour's worth of rant there, but I'll try to contain myself. The thing which I find very interesting about the current state of affairs is that machine learning has come a very long way from the first perceptrons that were around in the 1960s. Some of you may recall a book by Minsky and Papert called Perceptrons, in which they basically trashed the idea of neural networks because they weren't capable of understanding whether a graph, for example, was connected, because they were taking small bits of information and there wasn't enough data to reach a conclusion about connectedness. And so they basically said, these are worthless. And so there was very little work done in neural networks, with a few exceptions, who persisted over the course of some 30 years or more. Well, today, of course, we have multi-layer neural networks, and they are doing some pretty dramatic things. Our AlphaGo system from DeepMind learned how to play Go, for example, well enough to beat several grandmasters. And then they did something really amazing. It was called AlphaZero. They let it teach itself how to play the game of Go, and in 3 days, it became a grandmaster. Is that me or somebody else pinging? I don't think it's me. Okay. So in 3 days, which is pretty astonishing, and now they've explored other kinds of board games. So you can make these neural networks do some pretty amazing things. I'm sure you've seen the ones that do image recognition. Some of them are being used to distinguish cats from dogs. That's important if you're on the internet, because you don't want to mistake the cat video for a dog video. On the other hand, recognizing, for example, a cancerous cell or the presence of retinal, what is it called, diabetic retinopathy, looking at pictures of the retina, those sorts of things actually work extremely well. You train them using experts who will give you training sets for which the decisions have already been made, and then you run the neural network through the images, and you tell it yes or no, you got it right or you got it wrong. There's back propagation to adjust all the various weights in this structured system. Now, I'm not an expert in machine learning or multi-layer neural nets, but I will give you my cartoon model of what's going on, because I've been told that it's okay to think about it this way by the people who actually know how it works. The original single-layer neural network just didn't have very much state space. But when you look at a 100 or 500-layer neural network, there is an enormous amount of state space in that system. And so when you ingest all of the inputs from the samples that go into the system, you get to remember a huge amount of the information that flowed into the system. And so you have this enormous state space to work with. And the result is that you can train these systems to distinguish a wide range of different images or other inputs. So, for example, we use machine learning now to do language translation. Some of you will remember the early days of machine learning, where we would put a dictionary into the computer. I remember the French, it was a Russian English dictionary at Stanford. We put it in and thought, okay, this is easy. And then we put in out of sight, out of mind as the input, translated it into Russian and translated it back, and it came back invisible idiot. And at that point, we realized that there was more work to be done on language translation. Then we went to the statistical mode, where we had lots of documents that were purported to be the same document in 2 different languages or 3 different languages, and we used statistics. And even there, we sort of topped out at a not very good quality. Now we started using machine learning. And what surprised me is that instead of taking 100 different languages and building 10,000 different machines, to process in both directions, they built one very large machine learning network, and they fed it all the languages. And the result was better quality translation for all languages, even in the case where you hadn't trained a particular pair. Like suppose you had French to German, and you had German to Russian, but you hadn't trained French to Russian. If you just did those language pairs, and then you actually ran French to Russian in the network, you actually got something useful out. Not perfect, not without specific training, but there was something going on in this neural network that was absorbing the various expressions from these various language pairs, associating phrases with each other, even in the case that it hadn't been specific training. So this is pretty exciting. No, there was one thing, though, that you should be worried about. Some of you have heard about adversarial image processing. This is where you take an image of a dog, and the system says it's a dog, and then you tweak a few pixels in such a way that a human wouldn't really notice that the pixels have changed, and the system says it's a kangaroo. And you think, what the, WTF, how could that happen? And the answer is that in this state space that I mentioned to you earlier, there's certain places and some of the layers of the neural network where a few of the weighted elements are the place where a decision gets made or has a very strong influence on the outcome of the decision. And if you just diddle a few of the pixels, it causes that particular piece to go the other way because it had absorbed certain information from a small number of pixels in the images. And so the system can be fooled. We should worry about things like that because if we introduce a lot of machine learning into our into decision making about our daily affairs, it's going to have potentially negative impact in the event that decisions get made incorrectly. So there's a lot of pressure for transparency and a lot of pressure for explanation of why did the system make the decision that it did. So those of us who are working in that field have a lot of work to do there. They've also turned out to be tremendously useful, though. Some of you know that we trained a machine learning network to control the cooling system in our data centers. And somebody said, we used to do this once a week, and a human being would adjust all the various parameters. Our metric was how much power did it take in order to run the pumping system to cool the data center. Somebody said, let's train a neural network to do this. And we did, and it saved 40% of the power, which really surprised me. So, of course, we implemented that everywhere we could. Again, I'm conscious of time here. Let me just, again, tell you how concerned you should be, and certainly I am, about misinformation, disinformation that we see on the network. It's so easy for us to get trapped into some small part of the Internet's content and believe that either it matches our beliefs and therefore it's reinforcing and we don't pay any attention to anything else, or other people inject information into the system that causes us to feel as if everybody believes this particular conspiracy theory or this particular alternate fact. So we've just experienced this. The Europeans are experiencing this. And we should care a lot about that. There may not be a very good technological solution to this because you can always employ a botnet to reinforce whatever mechanical measure you might have of how many people believe this particular statement or this particular theory. And so the result is that a real need for critical thinking. And my view is that should be the most important topic taught in school, starting in the kindergarten and on the way up. People should get accustomed to asking questions like, where did this information come from? Is there any corroborating evidence? Was there some motivation for putting that information into the net? What could possibly have been that motivation? And those are the sorts of things that we should all be thinking about, but most importantly, our kids who will grow up in this online environment where critical thinking will be absolutely essential to making sense of all the massive content that's out there. Now, I don't have to tell you that malware and buggy code are big issues, but I want all of you who either are still programming or are responsible for other people who write programs to make them feel a great deal of responsibility for avoiding bugs and fixing them when they find them, especially before software gets released into the wild. I'm hugely concerned about this because for many, many years, all of us, including me, used to say, well, it's just a bug. It's just a mistake. So what's the big deal? We'll fix the bug. Well, the problem is that if the bug gets out there with billions of devices in the Internet of Things, some real harm can occur. A trivial example of that's a self-driving car that turns out to have errors in its software and makes bad decisions and runs into the nearest tree or does something else harmful. You can imagine other kinds of algorithms that could cause trouble, like program trading systems in the stock market, which behave like kids playing soccer, right? The stocks go up and all the algorithms buy stock, and the stocks go down, all the algorithms sell, and so you get these wild variations in the stock market. So I think that we need better tools for writing software that will help warn us when we've made mistakes, like you just created a buffer overflow, or you forgot to check whether this variable was set before you actually used it to make a decision. Those should be very straightforward, and yet I don't know how many of you have slapped your foreheads when you've discovered the mistakes you've made in software and thinking, how could I do something that stupid? And the answer is, well, you just overlooked something, and it would have been nice to have something sitting on your shoulder saying, you just created an overflow. What do you mean I created an overflow? Look at page number 123. Right? So that brings me back to ethics and software-based systems. I think we should feel an ethical responsibility to making sure that our software is well tested and carefully thought out before we release it. And that leads to digital literacy in general, which is the world's population understanding the frailties and weaknesses of software, the potential for misinformation in the net. All of those other things should be part of our normal training. When we learn how to drive cars, we actually have to pass a test to prove that we know the rules. And although I don't really think we need an internet driver's license, I think I kind of like the idea of somebody actually walking us through a series of experiences and testing to see whether we've understood what the risks are in using the internet and its applications. So this is the last slide, by the way, in case you were getting nervous. So the thing I want to emphasize is that the internet continues to evolve. It's still a very open environment. Technologically, I'd like to think it's an open environment from the sociological and application point of view. However, you all know that that openness is starting to collapse as countries react to some of the negative situations that you find in the net, and they're trying to protect the population, which is the responsibility of governments. But their protection may actually destroy the open utility of the network, and I really worry about that. So it's our job to make sure that we've done everything we can to keep governments from feeling like they have to lock the network down in a way that makes it far less useful. So open access and standards and applications foster GDP growth. It fosters, in general, the invention of new products and services. And surely, as part of the CENIC environment, we really want to improve the public's trust in the network. Safety and trust are really critical in this system. And finally, encouraging entrepreneurs to make use of this platform to create new products and services seems to me a very high priority. So I'll leave it there. I want to thank each and every one of you for what you're doing for CENIC and for your populations that you work with. I hope you'll keep doing that. And I certainly would like to return again, because I didn't realize what a terrific conference this turns out to be. I wish I could stay for the whole thing. I've got to go lecture at the Naval Postgraduate School this afternoon. But keep me on your distribution list, Louis. Thanks very much.